Drones. They're pretty hot right now, soaking up tons of venture capital funds. But you know what's more hot than a drone? A bird. The original drone, some might say. Also a dinosaur, which is pretty sick when you think about it. But we all know birds are not real. So today we're gonna work on the leg actuator for my bird robot project. Join me as I struggle to get not one, but two different types of custom electromagnetic actuators to work. There's laughter, there's tears, and there's more than a little bit of magic smoke.
Oh no. All right, so if you all recall from the last video, we left off with this prototype leg unit assembled, but not really tested. So it had the rolling contact joints, cable actuation mechanisms, and up here is where the linear actuators would be, but this is basically just a stand-in for what we need to build. And there you go.
Some of these parts may look familiar because in a prior video, I discussed how some of the aluminum parts were prototyped and machined on a 5-axis CNC. If you're interested in the manufacturing side of things, there should be a link appearing somewhere on the screen to that video. I used the same basic process for all the parts here in this video, so we're gonna focus basically on assembly and testing instead of the machining today. The star of the show, the first thing we're gonna work on is the coil for the leg actuator. I'm winding copper magnet wire onto aluminum bobbins, and this will form a moving coil in a voice coil actuator. More details on the reasoning around this choice a little later and the control scheme, but first we have to wind them. Anticipating a lot of coil winding in my future, I purchased one of these manual winders from China, and well, I probably should have saved my money. The shaft was too large for the bobbin, so I had to print a custom adapter. The winding mechanism is really crunchy, doesn't really work that well, and honestly, it's not a lot faster than just using a drill. The only perk really is the counter on the machine, but I basically ignored it once I got going. So yeah, just use the drill. After some struggling, I got the bobbin wound and wrapped it in Kapton tape to secure the wire and repeated the whole process. Each leg has 2 actuators, so we need 2 coils. Then it's assembly time. I first glue thin carbon fiber rods into the foot, forming 3 forward toesies and 1 rear-facing velociraptor toe. More carbon fiber is pressed into the ankle joint, which will form kind of the shin of the leg. Next, small bushings are pressed into the ankle joint. These bushings were made from glass-filled PTFE. The Teflon is low in friction, and the glass filler helps make it a little stiffer than unfilled polymer. Pins are pressed through those bushings and provide the rotational degree of freedom for each joint. I decided to use simple sleeve bearings here instead of the rolling contact joints that we saw in the prior video. I still want to get back to using the rolling contact joints. They're really cool, so that'll definitely show up in the final version, but it complicates assembly and also the kinematics if I get that far. So this prototype is focused solely on the actuation and the motor, and so I'm trying to minimize variables. Sleeve bearings seemed like a simpler way to get the job done as opposed to the rolling contact. Anyhow, the process is repeated until we get a mostly assembled leg with a few moving joints. Which means we can move our attention to the voice coil assembly itself. This whole idea came about because I saw how much space there was on the upper leg. A bird or even a human would have a pretty dense amount of muscle in that region. But most robots put a motor and a gearbox at the rotary joint and leave all that linear space unused. So I decided to put a linear voice coil actuator there instead. Structurally, they consist of permanent magnets and an iron shell or yoke. I already have this carbon fiber rod running through the area, so ring magnets are mounted on here. The bobbin is fitted with a PTFE bushing, which slides on the rod and is then inserted into the iron shell. When power is applied, the coil will move into or out of the yoke. VCAs are basically just a speaker coil, but they've been beefed up to use in positioning and high force applications. They respond linearly to current, so they're pretty straightforward to control, and can have both high force and high bandwidth. The major downside is that the stroke is usually pretty small. It's hard to build or buy a VCA with more than, say, 1 to 2 inches of travel. Usually they're a lot less. But we're building a tiny robot, so I figure it's fine. After that preliminary testing, I assembled both actuators and bolted it onto the hip joint. Finally, Dyneema cable is tied onto the actuators and routed down the leg to their respective joints. The final design is supposed to include springs to return the actuators and joints to their original position, but I wasn't sure quite where the springs needed to go or how much force they would need, so they were omitted for now.
All right, so we can see the setup here. We've got the leg and the 2 actuators. So the back actuator, like here, is responsible for extending the leg, and then at full stroke, it actually straightens out pretty significantly. And then the front actuator helps pull the knee back in and reset. So we do a stroke, straighten, the knee pulls that back in, and then back. It's not quite the motion I was hoping for. This front actuator, you can see there's a lot of slack here, which is not ideal. It comes off really easily. This is a pretty bad design. And when the leg's in this position, the front actuator doesn't actually do anything. This is just taking up space at the moment. It doesn't really engage until the leg is straightened out a little bit. And the back stroke has more angle here than I'd hoped before it starts to straighten. You can see the interplay between the 2 actuators when they're both running. If the front actuator is fully engaged, this back one basically can only move in this sort of pattern. It can't extend the leg fully into a straight line because this front actuator is keeping the knee bent. If we release the front actuator, then we have a chance to do the full extension. And if it's at kind of a half extension like this, the knee can change that angle. Okay, so this is the left actuator at 1 amp. And you can see it moves, but it's currently not really under tension. So this actuator doesn't really do much until the leg is straightened out. And then you can see it doesn't really have enough force at 1 amp. If we crank it up to 5 amps, it's enough to start to pull the leg back up. But it's not amazing. Clearly it's struggling, and at 5 amps, that gets hot pretty quickly and is definitely not sustainable. The back actuator will pull on the ankle joint and should extend the leg, but we can see at 1 amp, it doesn't really have enough juice to do it. If we turn that up to 3 amps, we're getting some motion. And at 5 amps, we get a full extension. There are some logistical issues. You can see that the cable is basically just tied to the bobbin right now. I didn't plan that out very well. There should be like a slot or something to capture the cable. The wires themselves are also just kind of coming off the sides. The whole actuator design itself, unfortunately, I don't think is going to work. So you can see this is basically a moving coil design where
The back iron and the magnets are stationary inside of this, and then the coil itself is what moves. I don't remember why I chose this design. I probably just wasn't thinking about it, to be honest, but this is not great for two reasons. The main one is thermals. So because the coil is what's moving, all of the heat is being generated inside this bobbin and coil, which is inside the case, and just doesn't dissipate heat very well. So this gets pretty hot pretty quickly and doesn't have a lot of airflow or surface area to dissipate the heat. The alternate design is called a moving magnet design, where the coil, so this, imagine these coiled copper wire would actually be up here stationary, exposed to the external airflow, and then the magnet is what's moving up and down. Moving coil designs are nice because the moving weight is pretty low. The copper and the bobbin are pretty lightweight, so it doesn't have a lot of inertia and can make quick movements. In contrast to the moving magnet design, because the magnets are relatively heavy, they're not quite as fast to accelerate. But in this case, I don't think it really matters. This isn't a super fast, speedy application anyway. And so we'd rather have the coils on the outside up here where they can dissipate heat better. Also, the gaps between the magnets inside of here and the coil to the back iron could be a little better. So I think I'm losing a lot of force due to just the physical arrangement of this. The front actuator is just not designed very well in retrospect. So the cable, you can see, comes out of the bobbin. It's supposed to route over this pin and then go through a slot in the joint and connect down at the knee. Just based on the way the kinematics are, this front cable has a lot of slack for a lot of the time, which is not great because that tends to get over here and it just comes off of its guide. When I was inserting the pin into this joint, I don't know how, but I managed to bend it on the arbor press. And so it's straightened up now, but you can see it's deformed the bushing quite a bit. And it's definitely not quite running as true as it should be. Not a huge deal, but this does have higher friction than it probably should in this configuration because the pin is no longer straight. It's kind of like a banana. And then finally, down here at the ankle, the cable comes under this pin and is held by this M2.5 screw. And that actually worked out pretty well. It's not the easiest thing to tension, but it's not too bad to give it a few wraps, tighten it to where you want it, and then tighten down the screw. So this I probably will keep for future iterations. It worked pretty well. And you can see here the front actuator is just tied to this pin at the front of basically the knee, and that's what pulls the leg back up on the backstroke. But I might route this cable under the pin and put it down, tie it somewhere onto the foot or the ankle, just to give it a little more leverage and deal with some of this slack issue. The last thing I want to mention is that right now there's no springs. So these are basically just flopping around by themselves. The final design, I think, will incorporate some springs on the different strokes. So a spring here to keep this tensioned up this way, and the opposite, a spring up here to keep this one tensioned down. If this ever becomes a working robot, there will be a ground underneath it, and you've got the weight of the robot pushing, compressing this leg structure. And so that natural force of the ground pushing, compressing this means that when we have springs in here, we'll be storing energy in the springs from the natural kind of resting state. And so the hopping motion will just be given enough energy to leave the ground, engage those springs, and then bring everything back to neutral before landing. Unfortunately, I think these actuators are going to need a big redesign. I don't think, even if we were to change it up so that it's a moving magnet and the coils are on the outside, I don't think they have enough force density in here to do what we need. We're pretty limited on space, and there's only so much I can do to decreasing the clearances between the various components. So I think what I'm going to do is go back to my very original plan from the first iteration and use solenoids rather than voice coil actuators. Solenoids in some ways are simpler. They have fewer parts. There's no magnets. It's basically just an electromagnet. They have higher force density, less linear force output, and a shorter stroke. So we'll see. I need to play with CAD a little bit and see if we can get something in here that'll fit. I recently discovered these. Manzanita Sol. I'm sure that's not how you pronounce it. It's apple juice, but it's carbonated. I think this is the best thing I've ever had. Oh, it's so refreshing. I'm not sponsored by them, but I would. Sponsor me, Manzanita. Oh, that's so good. Okay, so we are going to be assembling a rotary solenoid. It's kind of like a solenoid, but it rotates instead of going up and down. Or, well, it also goes up and down. You'll see. So there's a couple components here. The aluminum parts. These are basically just to attach it to the robot. So we're gonna set these aside for a moment and focus on these. So this is essentially the guts of the rotary solenoid. The main components are all in steel. This is 1215 because we need a low carbon, soft magnetic metal for the case and the armature, because the solenoid is basically an electromagnet, and so we need some iron in the system. So the setup is pretty simple. There is the case, which you can see here. Basically just a thin-walled piece of steel. There's an M24 thread on the back. And on the front, there are these slots, which are about 1/8 of an inch, because those are for bearings that will sit in those slots. Then there is a coil holder, which is basically a shaft with a back plate and a matching thread to go here. So this will screw into the back of the case. And then there's the armature, or like pusher plate, which goes on the top. And you can see it's basically just a plate with some holes to attach to accessories, and then slots that match up with those slots. You will notice these slots are a little different between the two, and I'll zoom in and describe what's going on here. So if we look at the case, you can see that the slots are basically full depth from start to finish. It's a nice spherical profile along the bottom, and there's not a whole lot going on there. It's just a simple slot. But if we look at the armature plate, you'll see that it's full depth on one side, and then it tapers out at the top end. And it actually gets more shallow. So this whole thing is at an incline, going from deep to shallow. And the reason for that is because of where the ball bearings sit. So you can see at one end, they sit at full depth, and then as it rotates, it comes up about 2 millimeters. So there's a 2 millimeter incline from top to bottom. And this is how it converts the up and down motion of the solenoid into rotation. As the plate is pulled against the matching slots over here, the ball bearing has nowhere to go except for around. And so as it rotates this way, it forces the top plate to rotate in the opposite direction. This will become a little more obvious once we get everything all hooked up. But I wanted to show you kind of the internal guts before we assemble so that you could see this action. Like a voice coil, this solenoid needs a wound coil. So unfortunately, we are back to this terrible coil winding machine. The next step, I believe, is to put the case on, and then we'll do the shaft and the bearings or bushings. Let's see, I think I want, yeah. There's one strand of wire that's sticking up and getting in the way of the thread. Alright. Definitely gonna use a bobbin, I think, next time. Okay, so next step is the bushings. I'm gonna take a shaft. It has a circlip on the back, and we're gonna put a spring on it. And that will go through the back here. Oh, and push out all of the bushings. Nice. Okay, never mind. The spring is too small. I need a washer or something. All right, so I don't have a washer that fits. So we're gonna use a nut, which it's dumb, but it should work. Pressed in a bushing on the top armature plate. Thread the wire through one of the holes and push it through there. Okay, now the trick, I need to get 3 of these ball bearings in while keeping this whole thing situated. Need to put a circlip on. So here it is, assembled, but we're not aligned yet. Oh. Right, I think there's a design flaw here. So there's a problem here. I noticed the diagrams, they always use a torque spring here. So it makes a rotational torque. And I didn't have any, I have these compression springs. So I thought, sure, we'll just use a compression spring, same idea. The problem is the compression spring, since I have a circlip on the backside and the front side, it's not providing what I want, which is to push this plate forward because it's not pushing on anything. The compression spring needs to have a circlip that's underneath in here to push on the plate, which I don't have. So it's not actually doing anything useful at the moment. We can fix that. We'll have to disassemble this again. All right. But yeah, I see why they use the torque springs. So maybe next design iteration I'll use those. All right, let's back that off a little bit. And, ow. Ugh, I hate circlips. Okay, so this comes off. Now we need to put this on the inside. No. Oh, no, okay. Problem number 2, I see some of the insulation already coming off on this top part. I should have drilled a hole or something on the side here to get the wire out, but I did not. Wow, this sucks. This assembly is not very fun. I've taken it apart again for like the 100th time. Basically, when I unwound it from the coil winder, it lost tension and everything kind of fluffed a bit. And I think I overwound it. So there's too much coil in there, which means that when the armature plate goes on top, it's making contact with the coil underneath and it's just causing a lot of friction, which is keeping it from rotating nicely, which is unfortunate because there's not an easy fix for that. So I think what I'm gonna do is just ditch the spring, put the armature plate back on and test it just to make sure the coil is working, just so we can see it doing something. It won't reset automatically because of the friction, but we can at least see if it's working. And then we can start on the next revision. There's a couple things that need to change. There need to be holes for the wires to come out of. I think I probably will just make a bobbin to wind it on because that'll solve a lot of these problems, keeping everything where it needs to be. Okay, let's do this. Still have tons of friction issues, so it's not working great, but it does do something now. So we're not rotating, obviously. Clearly, there's a lot of work left to be done. Hot, it's also really hot. This next attempt, I turned up a quick bobbin. So this is just made out of nylon, nothing fancy. I've tried to 3D print these and it just doesn't work because it's so thin. The print always breaks along the layer line. So just a quick thing out of nylon, and it will essentially sit inside of the housing like that. And we can wind this with wire first, make sure everything fits, and stick it in. And hopefully we won't have any issues like we did last time with it, the wire getting in the way of the armature. I also popped 2 little holes into the exterior of this case so that we can get the wire out of the bobbin rather than trying to snake it out the back and the front. Bobbin's in there, coil's wound. How many times have we done this?
Okay. All right, so I've put a circlip on the inside as well as the outside, because I think the problem is that when the solenoid pulls it down, there's nothing resisting, like forcing it to turn. And so it's just, you know, moving down like a solenoid. Whereas the circlip now will keep, it can obviously still rotate, but when it comes down, it's pushing against the shaft, and the shaft will be circlipped on both ends, so it shouldn't really be able to move. And hopefully we'll make it spin rather than change lateral position. Okay, so we can get a single motion, but it doesn't reset. So we can, if we manually move it over, so it's rotated fully, and then it'll rotate when we actuate it, but it doesn't reset. It just goes up rather than back around. Right, so I think this is the two design features that I neglected. I didn't think they were important. Apparently they are. The shaft needs to be splined into the armature plate, press fit it into here or something, but the shaft and the armature need to rotate together. And the second problem is that the spring I used, all it's doing is moving the armature plate back up, and we need it to rotate. And so I had gotten springs like this, some torque springs, but these are not what I need. This didn't actually really work. We need some type of torque spring set up on the back shaft here that will interact with this back plate and essentially rotate the shaft back into position rather than the compression spring inside of it pushing it up. So yeah, that's important apparently. Because what's happening is if we're reset, it's fine. It'll rotate as we want while the solenoid is actuated. But then when the force is released, the compression spring will just push it straight back up rather than forcing it to rotate back around. And then that just leaves us in a position where we're a solenoid is just going up and down. So that's dumb. Also, there's a short over here on one of these wires. If I push it in, we can get it to actuate, but when it pulls out too far, it makes contact with the case. Presumably both of these are, and it's just shorting out through the case. Ugh. All right, so you can see what I did on the backside. It's ugly. So basically I've got a screw here, a spring connecting the shaft, and it acts as just a little bit of a torque spring. It's really janky, but it's enough to give it some return. So between the shaft being pressed in, so the shaft is integral to the movement, and then the torque spring to return it back to its original position, we've got something approaching good. It seems to be working. It's also smoking. Woo! Okay, that's too much. I think it's working. All right, let's see how this does. Yep, that's not good. Oh no. So here's the insulation on the magnet wire. You can see that it's basically shot. It's completely melted off. All of the strand on both sides. That's just bare copper.
That's not great. And if it's like that on the outside, it means it's probably melted on the inside. So, I don't know. That might be it for this one. So I think this is the problem why it was working when it was horizontal, but not now that it's vertical. You can see the gap at the top versus the bottom is a little different. There's a little bit of play in these bearings. Not a lot, but a little bit. There you go. You can see it's got a little bit of slop there. The inner bore is a bit too large for the bushings, and so there's a little bit of play, which lets it wobble. And I think what's happening is that the inside boss on this armature is actually rotating down and making contact with the inside of the case, which means it's basically like magnetically shorting itself out, and we're not getting really much rotation. I think it's a mechanical slop issue now, in addition to, the other problems, but I think that's the current main problem, which is why it was working when it was flat, because gravity was keeping everything aligned. But now that we're up this way and the weight of this arm is kind of pulling it downwards, I think that's what's going on. So we need to fix the tolerance on the bushing ID, and then also probably leave a little more clearance between the armature and the case, just in case, and help prevent this issue from happening.
Okay, so gonna be honest, at this point in the project, I was fairly disappointed. I was kind of mad. I was kind of tired of all this not working and working on it. So I kind of shelved the project and moved on to other things that have since shown up on the channel. This footage is actually quite old at this point. But I did purchase a few rotary solenoids from eBay to take a look at. They're really cool little devices, and the manufacturing details are pretty neat. The armature plate is just stamped, and that includes the grooves that the little ball bearings ride in. I thought that was a neat detail because it's a lot cheaper and more efficient than machining it like I did. There's a nice little clock torsion spring at the back to provide the return motion, and overall the whole thing is just really tight and snappy feeling. It's a nice mechanism. So my original plan was to tear these apart and get some insight into how they work and how the coil and the armature were designed, stuff like that. I wasn't actually going to use them, but looking at their size, I think they might actually be a good fit for the robot. I don't have to DIY everything, right? I sometimes get it in my head that these projects aren't fun unless I make everything myself, but that's silly. I mean, I should just use these solenoids. They look like they're going to be a good fit. And if it keeps the project moving, that's probably for the best. In any case, that's where I'm at right now. The BirdBot is sitting in a box somewhere since I'm still doing the cross-country move thing, but I'm hoping to get back to it and work on it sometime in the future, and maybe we'll get it hopping around. Okay, well, I think that's all I got for you. I hope this was interesting, and I'll see y'all next time.